Stanford University.
It's really my pleasure to introduce our next 4 speakers who are new postdoctoral fellows here, and they happen to be part of a relatively new program that's called the Stanford Energy Postdoctoral Fellowships. And you can see the speakers here: Yukio, Kyle, thank you, Jack, and Sang. And they're going to go in reverse order for their talks. So this is my first time meeting them as well, so it's fun. All these talks are going to be on batteries, different aspects of batteries, because it is such an important area for solving the energy transition to renewables and to low energy, low carbon sources as well. So just a brief overview of the program. This is actually a program that was launched and run by Yi Shui and Audrey Yao, who is in the next door session. So she can't be in 2 places at once. She hasn't figured out how to clone herself yet. So you have me instead. And so this is the leadership team here, Yi, Audrey, and Rachel, who does a lot of the program management. And this program really is to create and to nurture the next energy leaders. And so with that, it's different to other postdocs that you might have encountered in your life, in that they're not going to be confined to the lab or to the bench or the office as such. They're going to be let out, but not just to roam free. They're going to have different programmatic elements that they'll be engaged in. And maybe they can talk to you more about that. An important part of this selection is this advisory board and the leadership for this program to help guide what this program looks like and how best to engage the postdocs with things in the world that would help them become leaders. So you maybe saw some of these people today and some others that are old friends that are not able to get away from us yet. So it's really a great program. So the goal is, I think, to fund and to award about 8 to 10 fellowships each year. And so they just started awarding them last year, I believe. And by the end of this year, I think they want to have about 18 fellows. And the idea is they'd all interact with one another, and they're working on different topics. So that would be one mode of learning. Lots of other things you can see here that they've been engaged with. That looks like a lot of fun activities. And the idea is just to connect them, help them learn, and give them the resources so they can become great leaders, like some of the folks you've heard from today as well, who are really great examples of what leadership in energy looks like. So just a final word from me, and then I'll hand it over to our speakers here, and just to say thank you to all the people who've supported this, and you can see them listed here, and particular Dai and Lee family donors, as well as the Tomcat Center and Precourt. So with that, I'd like to ask our first panelist to speak.
Hi everyone, my name is Sang Cheol, and thanks Jenny again for the really nice introduction. Really happy to be here today to showcase some of my research. My research is on batteries, and particularly on electrolytes and interphases for electrochemical energy storage. So I'll give you a quick sort of background. I think by now, today, you've heard many, many times how important electric vehicles will be in this energy transition. And of course, they are on the road already, but to accelerate the deployment of EVs and also to enable and decarbonize other sectors of the transportation sector, such as aviation and long-haul trucks, better batteries are needed. So this is a quick schematic of what's being used today, the lithium-ion batteries, composed of mainly 3 or 4 materials, the cathode, anode, and the electrolyte. And as you are all aware, the cathode and anode materials, they're sort of serving as the hosts for lithium ions. And they are very important in dictating the energy content or energy density of your battery. But the electrolyte is also extremely important. It's responsible for transporting ions across the 2 electrodes in lithium-ion batteries. As we go to higher energy density battery chemistry, such as the one shown here, the anode-free lithium metal battery, turns out the electrolyte becomes even more important. In this configuration, you can see the lithium ions, the yellow dots of lithium ions, initially stored in the cathode materials. Upon charging, they will be transported to the anode side and get deposited as metallic lithium. And it turns out that the electrolyte really dictates the properties of these lithium. For example, using two different electrolytes, the deposited lithium's morphology is completely different. And with that, the performance of these lithium metal batteries will be very different. For example, the cycle life will be very short if you use conventional electrolytes, but these highly engineered ones, they can last much longer. So electrolytes are super important, and that's why I've really focused on this topic during my PhD. So I've taken sort of three big different approaches for studying the electrolyte. One is trying to develop novel characterization techniques. So that is really the bottleneck and key to having a better understanding of these electrolytes. So I did a fair bit of that. And then secondly, to use some of these insights and techniques to design new electrolytes, better electrolytes for lithium metal batteries. And sort of these two first approaches were bottom-up, sort of really approaching the electrolytes from the molecular level. But I've also taken more of a top-down approach using some data and data-driven approaches to analyze and design electrolytes. So I'll quickly just hit on the high points of each of these approaches. So first, talking about the characterization technique. So solvation energy, you may not be so familiar with this term here, but essentially what it describes is how strongly the lithium ions are interacting and binding to the surrounding species in the electrolyte. For example, the solvent molecules, there can be anions as well. So how strongly they interact. And that is, of course, a very important parameter that describes electrolytes that affects many battery performances such as cycle life and the fast charging capabilities. But until now, or until very recently, that characterization had been much reliant on simulations, computer simulations. While they're very useful, we would want experimental methods to probe these very important parameters as well. So I won't go into all the details here, but using a relatively simple electrochemical setup, we can actually probe at these solvation energies of different electrolytes. And one really key and cool, interesting finding that we had was that, so at the bottom axis, what we have is the cell potential, or essentially the solvation energies. And on the vertical axis, we have the Coulombic efficiency, which is a measure of essentially the cycle life of your battery. And we have this nice correlation, which tells us to improve Coulombic efficiency of your batteries, you want to have weaker solvation. Essentially, the binding between solvents and lithium ions, we want them to be weaker. So that's one piece of sort of my research. Moving on to the next one. Transport, ion transport is, of course, a key property of electrolytes. And here we sort of introduced this high entropy electrolyte where we actually tune the entropy of the electrolytes to boost transport properties. So until recently, until this work, really entropy had been more or less neglected in battery electrolyte design, but we showed that actually by tuning entropy, you can significantly tune how the ions behave in the electrolyte, and then with that, we can increase very significantly the ionic conductivity, and with that, of course, the fast charging performance of these lithium metal batteries can be very, very different as well. So that was on sort of the molecular level design of electrolytes. Lastly, what I'll hit on is the machine learning study for our electrolytes. So just to quickly show you the flow of what we did. There's significant buildup of data in the literatures on different electrolytes and also how well they're performing, their performances. So what we did was build a data set using these literature data and extracted key features from these. And then we built machine learning models based on many algorithms, verified these models, and then extracted key insights, which actually led us back into the lab to design new electrolytes based on these insights and analysis from these machine learning algorithms. and design new electrolytes. So what we did at the end was sort of just really high performance, high Coulombic efficiency electrolytes that were essentially driven by these machine learning models. So that was my PhD work on electrolytes. And while electrolytes are really, really important, also basically still all of these electrolytes will have certain side reactions with a very highly reactive lithium metal. So in the ideal case, if you can have a protective layer that can really protect the lithium metal from these the electrolytes and side reactions with the electrolyte, that would be really the ideal case. So what we found as sort of our preliminary results was that using a material called hexagonal boron nitride, it's a 2D, two-dimensional material, as a protective layer on top of the lithium metal, it can really, and doing some engineering on that, it can really selectively transport lithium while sort of rejecting all the other ones that we don't want to contact with the lithium metal. So it's really serving as an artificial interface layer. And with that, we've seen actually some quite promising preliminary results with very high Coulombic efficiencies. And we'll be working on this during my postdoc fellowship to really combine elements of 2D materials, the highly advanced analytical techniques, also molecular engineering, which is what I just showed you about the electrolytes, and combine them all into the realm of electrochemistry to provide essentially better lithium metal batteries. So with that, I'd like to end with acknowledgments. My PhD advisor, Professor Yishui, my two postdoc hosts, Professor Steve Chu and Dr. Yang Kai Tseng, and all the important collaborators during my research. And thank you very much for the funding sources and your attention. Thank you.
Yeah, my name is John Holoubek, also a Stanford Energy postdoc fellow, as we all are. Yeah, thank you for showing up. I imagine you've been in this room or a room like it for the entire day. So hopefully this is engaging enough to warrant your continued attention. Again, you've heard a thousand of these today, but emissions are going up, if you haven't heard. Yeah, we don't want to stop driving cars and watching TV and making stuff, so we need to find a way to do all of these things more sustainably. The way that we've kind of bet on this, or bet on reducing these emissions, is electrifying sectors that are currently emitting. This is just an example of kind of what we could expect in terms of emission reductions for the US. It's a projection from NREL maybe 5 years ago, 7 years ago. Again, I'm not going to stick here too long. But this is the example of how we do things right now. Virtually all of these sectors, the reason they emit is because we were relying on a transition between chemical and heat energy to drive these technologies. We're really good at doing this. Engines are great, really good at building turbines, all of this. The only issue is that the source of that heat energy also produces CO2, if you're lucky, among other things. So to reduce this, of course, we need to switch to more sustainable sources. I think solar and wind are kind of some of the more promising sources, as at least we think currently. Photovoltaics and wind turbines let us transition this from solar and kinetic or wind energy straight to electricity. And again, we have motors and we can pass this electricity directly into the grid. That's fine. The problem is that solar and wind are not inherently stored in the way that fossil fuels are. Fossil fuels are awesome. You can burn it whenever you want and get the energy on demand. So what this necessitates is an intermediate storage step. Maybe many of you, like us, think that storage step is likely going to be next generation batteries. A battery is simply a way to transition between electrical and chemical energy, which if you were to drill into most of these emission sectors, you'll find that the missing transition that we need to be able to hit reliably and efficiently is electrical to chemical. Or if we could, then all of this could be electrified. economically as well. So electrochemical devices let us do this. The electrochemical device that has seen the largest amount of commercial impact recently certainly is the lithium-ion battery. But virtually all electrochemical devices look something like this. We have solid electrodes by which electrons can be passed, and they're separated by an ionically conducting electrolyte. These are most often liquids, cations and anions dissolved in some kind of liquid solvent. And in passing this current, we can drive reactions on either side that, in the case of a battery, let us either store or deliver energy. In the lithium-ion case, at a very high efficiency. So we think, sorry, this is the kind of, I think every battery talk has to have a Tesla picture somewhere. Maybe you, that's mine. So we think that batteries, I mean, we've already seen that in the case of lithium-ion, this has really driven a lot of growth in the electric vehicle industry. And we think a similar growth can be had on the scale of the grid, particularly due to the decreasing price of photovoltaics. However, to continue meeting more EV demand, so to win over people that have not bought them already, maybe many of you have bought them already, we need to either increase range. So this at a battery level means energy density. We need more energy dense batteries. We need to make charging times faster. So I don't own an EV. Maybe the best that we can do right now is maybe 30 minutes to 80%. I think that's in the range of what is currently the state of the art. We'd ideally like to get this down commensurate with refueling times for fossil fuel cars. And on the grid, we just need to significantly reduce battery pack cost and or cycle life, ideally both. So it turns out, at least from what I do, almost all of these performance improvements can and should come from the molecular scale design. So if you this is a little bit zoomed in, the previous diagram, again, generic electrochemical cell. We've seen particularly in the last 2 decades, a substantial improvement in our understanding of the solid electrode materials. I think this is lithium manganese oxide. It's just density functional theory. Maybe the last decade or so, we've really started, particularly for the next generation chemistries like lithium metal, zinc, if you're a zinc person, we've really significantly improved our understanding of the bulk liquid electrolyte. I think Sang's work is a great example of that. Both in improving the chemistry and their resulting structure once they're dissolved. Liquids do have a structure, although not quite the same as a solid structure. But where our understanding is still really breaking down is at the interface. Again, this is a generic interface, so maybe if you're from lithium ion or lithium metal community, interface typically means solid electrolyte interface. But there's also a liquid portion of that interface as well. And historically, we call this the double layer. But whether or not you're talking about SEI or the double layer, both of these things are highly influential to the behavior of the device. So this is literally the area of space that these reactions are driven, whether that's intercalation, conversion, or any oxidation reduction in a heterogeneous electrochemical cell. It's similarly really, really difficult to characterize, right? We're operating on the scale of single nanometers here, or less. That's the kind of region of space that we're interested in. SEI can range a lot, maybe even to the micron scale. But certainly for the double layer, we're on this scale. And there's very, very few targeted design strategies at improving this region, right? Typically what we do is we adjust the chemistry of one of the bulk materials in such a way, and we look at the interface afterwards, maybe after cycling, or so on and so forth, and make kind of correlational conclusions about what we want after the fact. But if we want to really design these systems, we need to understand this region of space better. This is where the frontier of understanding is, at least in my opinion. So the way that I've kind of at least hoped to do this and continue to do this and did in my PhD was to really marry computational approaches and experimental approaches. So understanding at a molecular level in this kind of region of space, particularly for liquids, is extremely difficult. And in my PhD, I at least partially focused on expanding our toolbox in terms of molecular dynamic simulations in these chemistries to understand what the double layer looks like, how it behaves under finite bias, what the lithium sees in this region energetically, so on and so forth. And then most of my other work is all experimental, so these things can talk to each other in a way that at least I hope has been a useful contribution. So my previous PhD work, this is everything that I have done and hope to do in one slide. We looked at how this liquid interface behaves under kinetic strain. What I mean by kinetic strain is fast charging or extreme temperatures, and thermodynamic strain. In this case, I mean very high voltages. We were able to show some things, found that this kind of hybrid computational experimental approach is quite useful in understanding this region of space. And in my time at Stanford, all 6 months of it so far, what we started to do is really expand our toolbox even further into more diverse interfaces with a more sophisticated description of bias and interfacial conditions. We also started to look at these features in a more diverse set of battery chemistry. So this is aqueous zinc here. And then I am still interested in the solid portion of the interface in lithium chemistries being SEI. So we're kind of looking at a number of ways to improve and even utilize those chemistries in the future. So I might be over time, but yeah, thank you. The past 6 months have been really great, and I'm really looking forward to any questions afterwards. Thank you.
Thanks, previous speakers, really appreciate it. My name is Kyle Frohna. I'm also one of the Stanford Energy Postdoctoral Fellows. Really appreciate you all being here and for the opportunity to sort of convey the vision for my research project going forth into this postdoc. So I am working on sort of a multimodal microscopic toolbox to be able to understand electrochemical energy storage devices, the likes of which Sang and John have spoken about. And I'm interested in the application of large-scale or grid-scale energy storage to kind of combat the sort of intermittent renewable energy problem that was mentioned previously. So I like to start these sorts of talks here. My cohort has probably seen this slide a few times before. This is Turlock Hill. This is the only grid-scale storage facility in all of Ireland, where I'm from. It's about 45 minutes south of Dublin. And it's a pretty rudimentary approach. They cut the top off of a mountain. They made a lake. And when you have excess energy, you pump it up the hill. And when you need the energy, you let it flow back down again. The fact that it's sort of the only place in Ireland kind of tells you about the fact that it's not really very economical, although it does serve a purpose. And that is sort of that we need to store these vast quantities of energy if we want to stabilize our grid. So my background is actually not in electrochemistry or in batteries. My background is actually in photovoltaics. So I've kind of made a bit of a pivot. And so at least in the academic world, the photovoltaics industry is kind of making a transition from what I like to call kind of ordered semiconductors, like silicon or gallium arsenide, to more disordered semiconductors. And so what I mean by that is that in our traditional semiconductor space, we basically process silicon at extremely high temperatures, and we make these unbelievably pristine, beautiful wafers with extremely low defect densities that are necessary to make really nice photovoltaic devices. This sort of new generation of photovoltaics is sort of challenging this paradigm by creating solution-processed materials where you can sort of dissolve a few chemicals in a solvent, process it at maybe 100 degrees Celsius rather than 1500 degrees Celsius, and you're able to produce really nice photovoltaics. However, when you do this really quickly, you also create a lot of disorder. And this goes right the way from the atomic scale all the way up to the device level. And this has really important ramifications for both their performance and their long-term durability. And those things need to be solved if they ever want to compete with silicon, which is obviously this incredible juggernaut. So in my PhD, I developed a series of microscopy techniques to be able to study photovoltaics under operation. And using a combination of light and X-rays, I wanted to be able to understand what makes a specific region of a solar cell function at optimal conditions versus another region degrade. And can we figure out what is it about the atomic structure or the chemical composition that makes that happen? So just sort of a brief demonstration is, this is a particular solar panel, and I'm shining some light on the solar panel and changing the voltage. And we're basically able to, with this sweeping voltage, figure out that different regions operate at a much greater potential than others. If we then apply a sort of accelerated stress test to the material, we can see that some regions also degrade very differently to other regions. And we can kind of go in with our X-ray, for example, and go, what is it about the atomic structure of this point that made it degrade more than this point? And so just sort of one key finding from our work, we were able to produce a passivation layer on top of this material to enable it to have a much longer lifetime and a much more durable solar cell. This is the unpassivated film, and I'm basically stressing the film with light, and you can see in real time, dark basically means bad in these images. And so you can see very rapidly the darkness kind of spreads across the film and it degrades. If we apply a particular passivation, we're able to see that over the course of this short measurement that things are much more stable. But we were basically able to demonstrate with this passivation material that we're able to get an accelerated lifetime of more than 10 years for this technology. And given that this technology started with a lifetime of about 30 seconds, it's a pretty big improvement. It's still not beating silicon, but it's getting there. And I think that's really promising. So kind of the vision of my postdoctoral work is, can we apply a similar sort of approach to the battery space? And so the reason I think that it's useful is if you kind of look at a cross-section of a battery, batteries are sort of disordered and messy by design. If you look at any one of the electrode materials, in the sort of schematic that John showed, it's just a nice smooth line, but in reality, it's many microscopic particles wrapped up in some carbon and some binder, and the same is true for the other electrode. So really, when we're cycling a battery, we're cycling lots of independent little particles that all have their own behavior. And if we could understand all of these during a cycle, then maybe we could build a better model for how to make a better battery. So in terms of technologies that I'm interested in personally, I think two potentially useful technologies for grid-scale storage are sodium-ion batteries and aqueous electrolyte batteries, because they have a much lower cost floor in terms of the raw materials for making the battery than lithium does. Aqueous batteries still actually hold the majority of the battery market, and that's mainly due to like lead-acid batteries that are in your car. But they have some inherent flaws which make it difficult to put them into a grid-scale storage situation. For a battery that we want for the grid, we want it to, that was supposed to shrink. Well, imagine that this got very small all of a sudden, because we don't want it to be expensive. We also want it to not explode. And so safety is a really important metric. The bigger your battery system, the more catastrophic it is if something fails. We also want it to last an extremely long time, so many cycles. And ideally, if we're putting on our sustainability hats, we'd also like it to be kind of environmentally friendly. And we'd also like it to work well as a battery. And so one of the key challenges with something like aqueous electrolyte batteries is that they really don't have the muscle of a lithium-ion battery. The thing that makes them cheap and interesting, which is that the water in the electrolyte, also limits their performance. And they really don't have a very good cycle life. So I kind of want to use a sort of multimodal microscopic approach to understand all of the different degradation mechanisms in these batteries and see, can we nanostructure the material or add a particular additive in order to boost their performance and make them more relevant as a technology. So there's our microscope. I'm interested in studying things like formation. This is sort of when you first take a battery and you charge it up and discharge it for the first time. It turns out that the way that you do this has really profound long-term implications for the cycle life of the battery. And it's really not well understood, even in lithium-ion batteries, why this is the case. It's also a massive bottleneck in terms of the production. It takes days. I'm interested in degradation pathways. And then can we use these sort of models to predict from like a time equals 0 image of our battery how it will degrade or how long it will last? Can we use this to feed in to boost the performance and lifetime, and then ultimately design better batteries? So with that, thanks very much for your attention.
Hi, everyone. I'm Yukio, and I'm a 2024 Stanford Energy Postdoc Fellow, which actually officially started today. So I'm really excited to show you some of the work I did and what I'm going to do on the first day of my postdoc fellow. Yeah, so I have two titles here. My main title is called Sustainable Energy Storage, which I would like to enhance as everybody talk about how renewable energy is coming, emission is growing, but is the energy storage device itself is sustainable or not? That's kind of the question I wanted to propose here. And the minor title is very related to my postdoc works, which I'm gonna show at the end of my presentation. So another version of lithium-ion batteries, 3D structures, very complicated. You have liquid, you have oxide, you have graphite, you have polymers. But instead of all this nice picture of Tesla, I want to show you how do you think about a life of batteries right here, right? So this is a very nice schematic from Dr. Linda Gaines from Argonne National Laboratory. So it kind of like depicts how the mining, how the lithium-ion batteries start from mining to the manufacture and to the production and then eventually for the usage. And it also kind of show you where does it end. And a really shocking kind of like news for us now is from battery usage to recycling. Currently, we can only kind of recover 5% of the materials we have. And as you can see, we want more and more batteries, but is the materials we have, the reservoir that we have on Earth, really enough to really support our energy storage in the next 20, 30 years? So there are a few different of the recycling procedure or kind of the method people are looking for it. And then this pyro and hydro are essentially just treating the waste or lithium-ion end of the batteries as an ore and then try to extract the materials. But because this battery has so much complicated chemistry, it's very difficult to do this in economically practical way. People are excited about this direct recycling. Essentially what we're doing is, instead of treating this battery waste as an ore, let's disassemble the battery, and then let's separate the different materials individually first, and kind of recover or kind of reunite the different components. And my basic training is material scientist and a material chemist. And from this diagram, I have one thing that really doesn't make sense to me, is this battery shredding. So in order to recover different components, why are we shredding everything together and put all the mix together? This is gonna make make our life really hard, right? And there's obviously a reason for this. It's because this is another, maybe more realistic how the battery look like is the battery are designed in a way to optimize the performance that the structure itself is so intricate and everything is so tightly sealed, very difficult to disassemble in the autonomous way or in a very large scales. So in my PhD, I was thinking, hey, if our existing battery is already very, very challenging to do this in an economical, practical way, can I design materials to do this job? And then, as I said, I'm a material chemist training. So what I have been looking at is this very biological phenomenon called self-assembly. So what does it mean is when you have this phospholipids, which is kind of like a fat acid, you have one side that like water, you have one side that doesn't like water, they'll self-assemble into a membrane. So this is kind of like how our cell membrane look like. And I was able to change the amphifill chemically, synthetically, and then to design battery materials. As you can see, I started as individual molecules, and then if I let them kind of like sit in the water, they'll form this nanoribbon with a lithium-ion conductive feature, and eventually I can process them into a solid-state kind of self-standing membrane. And this picture showing you here is about 30 micron thick. And then we are really fortunate to talk to our industrial collaborator, and then the first thing they ask is, can you make this 10 nanometers? I was like, okay, give us maybe 3 more years, we'll try about it. But the idea here, as you can see, is if the current recycling industry having the trouble, can we design material to facilitate the process? And then I'm still very excited and motivated in this direction. But in the postdoc, I thought about something else that, hey, if the metal, if the cathode material in the battery is the valuable part and it's very kind of like critical materials, can we use something that's abundant, very, very rich in the earth, and then to make it work? As on the left side, I'm showing you kind of like energy density map. So you can see on the horizontal side, it will be showing you the lighter the cell weight, and then the vertical side, it's a smaller the cell size, which the same amount of energy stored. So as you can see, this cyan color, lithium ion, I believe the Tesla or any electric vehicle car is about the right top. So we are hitting the theoretical limit for lithium ion battery. That's the reason why the whole community are so excited, so motivated to try to come up with new chemistry. And then the reason I'm looking at a lithium sulfur is not only you have a higher energy density, but it's very cheap. So sulfur is a byproduct for copper mining, and then people usually want to get rid of it. So as you can see, I put a number here that sulfur cathode is usually about 10 cents per kilogram. I'll just give you a sense for the NMC, LCO, any kind of metal oxide cathode we are using today, it's about $20 per kilogram, even in the state-of-art industrial scale. So you can see there are hundreds times of difference. And in the actual battery manufacturing, 50% of the cost is actually from the cathode materials. Nevertheless, the lithium sulfur battery people have been fighting or combating for about 30, 40 years. They have been tackling a main issue is this something called polysulfide effect, a shuttling effect. What's happening here is the sulfur, the yellow part, will start to move around when they are chemically react to the intermediate state. And when they move around, they will come to the other side of your battery, and your battery start to degrade. So we have been fighting this for 30 years. We still have not come up a conclusive idea to kind of preserve this. So my proposal is, okay, instead of using liquid here, let's use something that completely block this kind of intermediate compound, which is this all solid state. So complete here, gonna be solid state. So as you can see, not only you can expect a little bit higher energy density, but potentially you can completely prevent this effect. And the proposal here is, well, this thing is not there yet. It's mainly because the interface or the kinetics is not really doing a good job. So as you can see here, everything is happening in this very thin layer of interface, as we have been already discussing the whole day. And for the reaction of this happening, somehow this solid state setup is just not really doing the good job. So what I've been proposing is, let's put this electrode apart, and let's start with these three components. And if we can coat these components with some of this facilitate chemistry, and then put it back into the final cathode, so you can see this blue artificially constructed interface, I'm expecting them to facilitate the reaction of the kinetics. And then in terms of methodology, the main technique I'm looking at is atomic molecular layer deposition. So what's happening here is basically you kind of alternating different reactants and let them react in a sequential way so you can control this layer in one single atomic layer or a few to not only help the reaction, but also doesn't make it grow too thick to prevent the rest of the reactions. So at the end, I would really love to acknowledge my two hosts, Dr. Jagjit Nanda, who has been the lead at SLAC Stanford Battery Center. I'm happy to talk about later if you haven't heard about it. And also Professor Stacy Ben, who has been the expert in supporting the ALD techniques. And thank you so much for your attention.
Thank you. Thank you, Khalil. Wonderful. So we do have some time for questions, and if you don't mind staying a few minutes after 4:30, we can have even more questions. So yeah, why don't we go to you first? Do you have a microphone?
You mentioned ALD, it's a very slow process, right? Is it like economically feasible to use in the battery world?
It's a great question. I think there's a huge misunderstanding gap between the ALD kind of like 20 years ago versus now. The ALD has been developed back to 1960, And it has been a very expensive technique. But now these days, you can really coat very thin layer, like 1 to 2 atomic layer. I think what industry actually doing in, for example, our iPhone battery is coating this very thin 2 layer of aluminum oxide on the cathode to make the potential higher. So I think it is possible to make the ALD economically feasible in the process of manufacturing.
More questions?
Maybe a follow-up to that would be, I mean, do you think that with moving to solid-state batteries, we would be using more of like the processes that we typically use in semiconductor industry for battery processing maybe in the future?
I think that's a great point. That's why you see I'm introducing ALD, which is not new, but like trying to push this forward, right? I think battery has been growing in the past decades, but it's definitely not as mature as semiconductor industry. So I think there are a lot of things we can learn from not only semiconductor industry, but also maybe aviation, airplane industry. That some of this, not only the manufacturing, but also fundamental science could be applied to make the better batteries. Yes.
While you're thinking about another question, I'll ask a couple of questions. So you're all working on different aspects of battery research, and so I imagine you've had a chance to talk to each other a little bit. So what have you learned anything from each other for a start? You come from very different backgrounds, so have you already learned something from one another's research that has been useful for you in thinking about what you're doing? Yeah, whoever wants to go first.
I can kick us off here. This one of the really nicest things about this program is that we have somewhat regular meetings. For example, I think you saw some photos of lab crawls. Essentially, we go into each other's labs and take a look and have discussions about the research. And from those meetings, I think it's actually quite interesting how we can not only learn from each other, but generate also ideas in those sessions. So I think this this fellowship is a very unique mix of people all working on energy, but they come from sufficiently different angles, so that I think there's a really good synergy here, and we're obviously very thankful, I think all of us are, for this opportunity. Yeah.
So related to that, I'm going to do a little bit more on your work. Mm-hmm. So what is the most challenging part of your work that you've so far? I mean, we all know research is difficult, right? So you're trying to make it so that this technology that we really need for multiple uses, but for grid scale storage, for example, it can really enable us to put renewables on and give us power when move to lower carbon, and then for other uses as well. So what is it that you find most challenging? I mean, the science is cool, but at some point we have to think about this scale, the manufacturing, and nice to see someone's thinking about the recycling as well, right? So what, for you, in your work, what do you think is the most challenging part?
I can take a stab at it for sure. I think, for me, I'm very interested in sort of method development, to be able to develop new techniques to understand things in a better way. And I think what's really critical if the industry is going to take our results seriously is that we don't sort of dismember the battery in such a crazy way to just get an experiment over the line. I think whatever cells we measure should look exactly like the real cells. I think we've learned a lot in the battery literature with these sort of heroic experiments where the battery is so almost not a battery, but it is. And we can learn a lot from that. But I think if we want to make real kind of impact in the short term, the cells have to look exactly like the real cells. And that makes them very hard to study because, as sort of Yukio said, for example, they're extremely compacted. There are many layers that are normally opaque, which if you're trying to study with light is very tricky. And so designing experiments in a way that industry would care about them is very tough.
Interesting. Wonderful.
Thank you for a very nice talk. So I have a question about the solid-state battery. So when switching from lithium-ion battery to lithium metal battery, how much more lithium are needed, and what are the implications from the supply chain side? Because lithium metals are already challenging in terms of supply. Thank you.
Question to me, right? Yeah. So you're saying when transition from lithium-ion to solid state, but our lithium is also gonna be more and more critical these days, right? And then the price is fluctuating a lot, and then you have okay. So yeah, that's a great point. I think lithium is definitely this love and hate relationship in terms of they just simply give you the highest energy density and the highest potential. Lowest potential, so you have a higher energy density you can harness. I think there could be at some point that different battery chemistry are designed for different applications. So for something like EV, for something like electro aviation, we still need very compact, high energy density energy storage. Then that's the case, we're gonna still stick to lithium. But for some of the large grid scale, I think aqueous system, sodium system could be a wonderful alternative option. Yeah.
Sorry, can I follow up on that?
Yeah.
In terms of solid state, in particular, I mean, any lithium metal chemistry, we haven't really nailed down what the cell is going to look like yet. But in the case of solid state, I mean, the lithium ion demand, like literally how much lithium is in the cell, is going to depend on essentially how much we can get away with in terms of how thin the electrolyte can be, how much excess lithium metal you have to use on the anode side, so on and so forth, to get kind of the cycling performance that you want and the safety features, and et cetera. But in principle, if all of these things shake out how I think we want them to, per unit energy, lithium metal should actually be less resource intensive than lithium ion, because every lithium in a lithium metal cell gives you more energy, if you want to look at it that way. So I would say that the ceiling should be better, but we don't know enough to say anything definitive.
Thank you. Sang, any follow-up to that? You're nodding profusely.
I think I'm good.
Yeah, very good. So we are, maybe, do you have a question over there, Chris? Last question then, and then we'll.
So this is really about imaging and the problem of looking at something as close to the real thing as possible. But there's huge advantages to looking at a surface rather than trying to dig into an interface. So I want to couple this with the question about what's happening in the first cycle and that forming reaction, if you call it that. And it seems to me that's a real interesting opportunity, because you can take apart the battery before you do that, and you can take it apart after. And it seems like just by differential imaging, comparing those two cases, you could learn a tremendous amount. Do you have anything to add to sort of flesh that idea out, if it's even not crazy?
No, I think you're very much in the same sort of headspace as me. I think if we're able to pick apart and really see what's going on, either at an interface, even at sort of well away from a battery design, as you say, there's a lot that we could learn. I guess ideally, if we could get away without disassembling the cell, that would be optimal, which is kind of what I'm trying to do, in the sense that these interfacial layers or solid electrolyte interfaces, they're so sensitive to their environment that the act of disassembly could well change them. And so if we can sort of in situ or in operando see these things, I think it's a really interesting opportunity. I totally agree with you.
Yeah, wonderful. And with that, I've kept you 5-6 minutes longer. So thank you so much for your patience and for staying. And one last thank you to our panelists, to Sang, Jack, Kyle, and Yukio. Wonderful.